Okay, so let's start our discussion of evaluation test 1 from the MCQ paper. So we are discussing today 10 MCQs. Yeah, look at the first one. Which of the following statement is correct regarding the experiments related to atomic models? Okay, atomic models. So in atomic structure lesson, we have two main areas. First part about the atomic models and second part about the periodic properties. Okay, and here it's asking about experiments and related theories to atomic models. Okay, so we have 5 atomic models we know. We have a Dalton golf ball model, then Thomson plum pudding model, then we have Rutherford planetary or nuclear model, then we have Bohr model, finally we have quantum atomic model. Okay, so here these experiments, these findings they have given are related to these atomic models, right? Look at the first one. So you have to ask, they're asking the correct one. That means, Laman, 4 statements here are incorrect, right? So when we write the review, what should we do? We should write in front of the incorrect ones why it is incorrect, and then write the correct way of that statement. For example, take the first one. Anode rays are produced from anode. Okay, so that is a very common MCQ point we saw in our early papers. Anode rays are not produced from the anode, no? So therefore we can say this is wrong. Then we can explain where it is produced from and why it is wrong. Okay, so anode rays are not produced from the anode. So anode rays are produced within the medium, not from the anode. Okay, so you have to explain that one. Okay, this is where the anode rays are formed like that. Okay, so I'll take that diagram, cathode ray diagram. So then let's say this is our cathode and this is our anode. Okay, so cathode rays, or in other words, we can say electrons are moving from cathode to anode. So we can say cathode rays. Cathode rays originate from or start from cathode. That's why we call it as cathode rays. Okay. But if you take anode rays, okay, anode rays are not starting from the anode. Okay, so where it is starting? Anode rays are starting from the medium. So I'll explain you the mechanism how anode rays are created. So when these electrons are passing, okay, so they can collide with the gas molecules. Let's say in our tube, we have hydrogen gas. First of all, that hydrogen gas will be splitted to hydrogen atoms. Okay, so that means this hydrogen gas, diatomic molecule, will be splitted to 2 atoms. After further collisions, this atom will create an ion and that electron will be released. So electron will move towards the anode as usual and that positive H plus ion created. Okay, so this is the positive place. This is your negative plate, no? So that positive H plus will move towards the negative cathode. So then if the cathode is having perforations, it means small holes, what will happen? This cathode ray, so this anode ray will move through that perforations. That is what we observe as anode rays. Anode rays. Understand? So that's how anode rays are created. So then you can have a nice idea. Even though cathode rays originated from the cathode, anode rays are not originating from the anode. You can see where anode rays are starting. It's starting within the medium. Can happen anywhere, right? But we say usually it is closer to the anode, right? So you can write in front of this anode rays originate within the medium. Medium near anode. Understand? That is the point. That is the point you have to write for the first one. First one is incorrect. Okay, now, so like then, write a complete review. This paper I gave you is not a very easy one. It is kind of a good paper meeting the exam standards. Okay, so then you can have an idea. So where you are now in these 2 lessons mainly, first and second lessons, you can see what are the problems you are having, right? So we have to try to correct those problems. Okay, so if some theory is not very gone to your brain, then you should repeat it. So it's a nice way to repeat that theory point, that whatever the area, you can easily and you can effectively repeat that one by writing reviews. Okay, so write a review about anode rays. Okay, this is how anode rays are working. And you can collect those papers and put a stapler and keep it with your paper. If possible, take a printout of the marking scheme also. For the structured essay papers, it will be valuable. So when you are going any exam in your school or in my even my class or even before the A-level exam, you can refer those reviews, refer those questions you did. That is the best and most effective way of learning. Okay, because you are finally going to write a paper of 5 hours to prove your knowledge. That's the final thing you are doing in the A-level. So we don't forget that. That means questions are the most important thing, and we should try to get as much as correct possible. Okay, so write good reviews. That's what I'm advising here. Right, now let's go to the second statement. Let's see whether it is correct or wrong. Second statement is, when alpha particles radiated towards a thin gold foil, only a few alpha particles had penetrated. When alpha particles radiated towards a thin gold foil, only a few alpha particles had penetrated. So this is coming from where? It is coming from our gold foil experiment. Gold foil experiment. Okay. In gold foil experiment, you are using alpha particles, true, and you are radiating it towards a gold foil. That is also true. But the problem is, the observation they have given is wrong. When you radiate alpha particles towards the gold foil, majority of the alpha particles are passing through the foil without any deflection. Okay, remember the number I gave you, 9,990 is passing without any problem. If you send 10,000 here, only few alpha particles are slightly deflecting due to the because it travels near the nucleus, and only very few particles are bouncing back because they straight away collided with the nucleus, or they experience an enormous repulsion from the nucleus. Okay, so that's what happens. Okay, majority is passing through the foil, so this observation is wrong. Understood? It says the other way. E over m ratio of cathode rays does not depend on the type of the gas inside the cathode ray tip. That one is correct. It's a property of cathode rays. Why? Okay, cathode rays are always electrons. Remember, cathode rays are always electrons. So, electrons, doesn't matter what is the gas you are selecting. It may be hydrogen gas, just like I took here. It may be oxygen gas, whatever. Right? But finally, what is going through the cathode ray tube as cathode rays is electrons. Because from cathode to anode, electrons are jumping. You understand? Here, you have I put a diagram for that also. This is the correct one. You can draw this diagram, okay? Cathode ray, and here you have your negative this is the power supply. So in physics, in all levels, you know, electrons are pumped from the negative electrode. No? So then these electrons are coming here and they are jumping from cathode to anode. Understand? So no matter what is the gas you put into this tube, it's always cathode rays are electric. Understand? So you can say for any gas, for any gas, cathode rays are electrons. Cathode rays are electrons. So it will move from cathode to anode. Okay? Right. So that's the explanation of the third one. That is our answer. Now let's see why fourth and fifth are also wrong. See the fourth one. Path of the cathode rays is not affected by both electric and magnetic fields. Path of cathode rays is not affected by both electrical and magnetic field. That is wrong. Why? Because you know cathode rays are charged particles. Okay, cathode rays are charged particles. So any charged particle movement will be affected by electrical and magnetic fields. Any charged particle movement will be affected by electrical and magnetic field. Okay, so you can write that one. Cathode rays will be deflected. Okay, so any charged particle, any charged particle movement is affected by electrical and magnetic fields. Electrical and magnetic fields. Understand? So they will bend and they will deflect. That will happen. So fourth one is wrong because cathode rays are negatively charged. No? So they must be deflected. And then look at the fifth one. Let's say why fifth one is wrong. Neutron was discovered by James Chadwick. That is true. By radiating beta particles. And that is the wrong part. It's not beta particles, no? So what is the particle used by our James Chadwick? He used alpha particles, not beta particles. Understand, Lamai? So then you can say in front of the fifth one, right? Chadwick used alpha particles. Chadwick used alpha particles. So actually in our syllabus, there is no experiment. There is no experiment. It is done using beta. Okay, so gold foil experiment, this Chadwick experiment, both are done using alpha particles. Understood? Both are done using alpha particles. So you can write a nice descriptive review for the evaluation test, this MCQ. Then it will be a very valuable thing for you, Lamai. Please do it. Okay, and then in the class, I'm asking you to show that. Then show it to me and just see whether there is anything to be added or is there any mistakes you have done when you are writing. Okay, please show it and mark your review. Okay, right. Then at the second question, which of the following statement is incorrect with regard to with regard to ground state manganese atom? Okay, so there are 5 statements given. It's about manganese atom. Manganese atom. So when they ask a such question, we need our electronic configuration. Electronic configuration of manganese. Okay. So within the bracket, it has given Z equal 25. That stands for the atomic number. The atomic number is 25. Atomic number is 25. Z equal 25. So manganese electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5, 4s2. This is the electronic configuration of manganese. So manganese atomic number is 25. So that 5 comes here. That's how I taught you. Okay. That 5 comes here. So this is your electronic configuration of manganese. Now let's see the statements. I hope you have the paper with you. First statement tells the electrons can be found in 4 energy levels. Okay, so are there 4 energy levels here? Energy levels are represented by this number we write in front of each English letter. Okay, so this number 1, 2, 3, 4 stands for the principal quantum number. In other words, it represents energy level. Okay, so you can see 1 to 4 numbers are there. That means you have 4 energy levels. Okay, so first statement is correct. Okay, so electrons are found in 4 energy levels. That is correct. So 1s2 in first energy level, 2s2, 2p6 in the second energy level. Okay, second energy level. Then you can say 3s2, 3p6 and 3d5 in the third energy level, 4s2 in the fourth energy level. So like that, first, second, third, and fourth energy level. Right. So that's a easy statement. And then look at the second. Second one tells electrons can be found in 15 orbitals. 15 orbitals. Right. So to get an idea about this orbital thing, we will understand what is this P6D5 means? Okay. So here, if it says 2s2, it means you have a s orbital, and in that s orbital, you have two electrons. That is the meaning of that now. When they say this P6, that means there are, in p sub energy level, you have three orbitals. In those three orbitals, you have 6 electrons. Understand? That's what it is meaning. Okay, just like that, you have here another three orbitals. And in d sub energy level, you have 5 orbitals. On those 5 orbitals, you have 1 electron per each. That's how d5 is represented. So this is the way of orbital thing is related to the question. So it's asking here whether there are 15 orbitals. We will count. Okay, we will count. Now in 1s2, you have 1 orbital. 2s2, you have 1 orbital. 2p6, you have 3 orbitals. So this altogether, this with these two, you have now 5 orbitals. Then 6th orbital, 9 orbitals, 9 plus 5, 14, and this one 15. So 15 orbitals are there. Okay, 15 orbitals are there. So second statement is correct. So here is asking incorrect one. So first and second statements are correct. You have 15 orbitals. Okay, you have 15 orbitals. You can write kind of a review. You have 1s, 2s, 3s, and 4s. You have 4 orbitals. Yeah. Then you have 2p and 3p. You have 6 orbitals. And then you have 3d. You have 5 orbitals. So altogether you have 50. You can write in that way also. Just be creative and write properly. And whatever the thing you write newly, just show it to me and see whether it is correct. Okay. Right. Then third statement, maximum 5 unpaired electrons are there. 5 unpaired electrons. You can see here, this D, you have 5 unpaired electrons. 5 unpaired electrons. So this third statement is then correct. You have 5 unpaired electrons. It's true. There is no unpaired electrons in other places. All orbitals are paired. Okay. Then fourth one, there can be maximum 12 electrons with azimuthal quantum number L equal 1. Okay, so what is this azimuthal quantum number? L equal 1 represents P sub energy level. P sub energy level. In P sub energy level, you have 2p6 and you have 3p6. You can see the configuration. 2p6 and 3p6. So you have 12 electrons. That is also correct. Okay, so then last one must be wrong. Let's see why the last one is wrong. The last statement, it says there can be maximum of 6 electrons with magnetic quantum number ml minus 1. ml minus 1. ml minus 1, magnetic quantum number represents orbitals. So we're going to write it here. Okay. So you have S, then you have P, then you have D. So these orbitals are marked or labeled by magnetic quantum number. So here the magnetic quantum number is 0. This one minus 1, 0, plus 1. -2, -1, 0, +1, and +2. Now you can see where the -1 present. Here you have a -1 orbital. Here you have a -1 orbital. So there are 2 orbitals now. Okay. So in your 1s, 2s, you don't have any s sub energy level. You don't have any -1 orbital. But in the p sub energy level, you have -1, 2 electrons. Okay, because here there will be 2 electrons now. In 3p6 also you have 2 electrons. In 3d you have 1 electron. It's not 2. You can see here. Only 1 electron is there. Understand? So altogether you have how many electrons? 2 plus 2 plus 1, you have 5 electrons, not 6. Is that clear? Okay. So that is the answer for the second question. So these are, you can see, that is exam level now. They are not just simple like questions. Okay. You have to think and study, and you have to prepare well prepared to write this paper. Okay. Right. So that is the second question. I'll share the question once again to get an idea. Here's the question. Right. So then after that, we are going to the third one. If the de Broglie wavelength of an electron is 200 picometers, its speed, the speed of the electron is. Okay, first of all, what is the de Broglie equation? De Broglie equation tells you this de Broglie wavelength is equal to h over mv. Okay, de Broglie wavelength. Okay, that means any de Broglie explained actually any particle, okay, can show wave behavior. And Einstein said any wave can show particle behavior. So it's finally we can bring together and say wave particle dual behavior. Okay, so wave particle dual behavior. Particles are behaving like waves. Waves are behaving like particles. So photon, which you learn in the Planck theory, is a good example to say that waves are behaving as particles. Okay, because in photoelectric effect, what is happening? Photons are coming and they're knocking out the electrons. So for that, photons must behave as particles. Understand? And then you have this wave, our de Broglie equation. It is showing you that a particle, something that has any mass, if it is moving in some velocity, it will have a wavelength. Okay, but for a baseball or something like macroscopic object, the wavelength is very negligible. Okay, so but for things like things very small like electron, proton, atoms, okay, they will have a good related to their dimensions, they will have a considerable wavelength. Understand? So like that, here it is asking to find us the wavelength of an electron. Okay, we'll see what it is telling. Huh? So yeah, de Broglie wavelength is given to 200 picometers. Okay, so 200 picometers, if you put it into meters, it will be 200 into 10 to the power minus 12 meters. That means 2 into 10 to the power minus 10 meters. Right, then, yeah, then we can use this to substitute and see. We can say the velocity is equal to h over m lambda. So Planck constant, the value you have been given here is 6.6. Okay, use that value into 10 to the power minus 34 joule cell. Then you have mass of electron 9.11 into 10 to the power minus 30, so minus 28 grams. So minus 28 grams, no? Okay, so here the mass is given 9.11 into 10 to the power minus 28 grams. So in this equation, Lamai, you can't put grams. Remember, it must be kilograms. Okay, otherwise the units will not get cancelled. Here you can see the joule unit is used. Joule is what? Newton meters. Newton means what? Kilograms, ms minus 1, ms minus 2, sorry. Okay, so they to cat you in this joule unit, just understand that in that joule unit you have kilograms, no? Right? So to cut that unit, you must substitute the mass using kilograms. Okay, so then we can prove that one in this way also. So if you put this m as the subject, lambda into v, now substitute the units, joules, joule seconds. Okay, lambda is wavelength meters and velocity ms minus 1. ms minus 1. So then this joule you can write like Newton meters. Newton meters per second. So Newton meters second and meters ms minus 1. And then you can write Newton is kilograms because F equal ma, no? Kilo m a is acceleration. Right? ms minus 2. ms minus 2 and multiplied by s and ms minus 1. See, everything will get cancelled. Everything will get cancelled. And then you have another m, no problem. M into second. Okay. Everything will get cancelled and you will get the answer in kilograms. So that means you must substitute this gram value as a kilogram value. Okay, so I think some of you might get this question wrong, right? So you must substitute kilograms. Just understand that. 200 picometer, you can say 2 into 10 to the power minus 10 meters. Okay, so then finally you can say 3.3 over 9.11 into 10 to the power is minus 3 to the power 7. 7 meters per second. Okay, so it is like 1 over 3. 1 over 3 into 10 to the power 7. So it is somewhere around like 0.33 or somewhere into 10 to the power 10 to the power 7. You can say like somewhere around 3 into 10 to the power 6 meters per second. Okay, so then you can see it's approximately taken by rounding it off. Let's see the answers. 10 to the power 6 is there in only one answer, which is the second one. Okay, so then don't consider about the decimal value. You can see how did I do? No, it's not a divisible one. Then I didn't went to divide also. You can select that one by looking at the MCQ answers. Okay, so answer is answer 2. I hope you all understood that one. That's a good question because of the units. I hope if you get this one wrong, the reason is not converting the gram into kilogram. Okay, so study that one and remember that one. Remember, if you get this wrong, just remember, okay, something like this happened in an exam. I didn't converted the units, so next time I must look at the units and do it properly like that. Just put that message into your brain, okay? Right. So next, look at the fourth MCQ, which is asked from the emission spectrum. Emission spectrum. Look at this one. ABCD represents the certain emission lines in the hydrogen spectrum, the correct ascending order of their frequencies. So you can see the energy levels. Energy levels are there up to 5th energy level. So I'm going to put a diagram that showing up to 5th energy level, 3rd, 4th, and 5th. In equal 1, 2, 3, 4, and 5. 5th energy level. And the transitions are like this, any from 4 to 2. First one is 4 to 2A. The second one is 4 to 1. Okay, 4 to 1, second one. And third one, C, is from 5 to 3. 5 to 3. 5 to 3. 3 is right here. Shorter one. Then you have 2 to 1. These are the transitions. A, B, C, D. A, B, C, and D. These are the transitions, okay? Now look at the question they're asking. It's asking you to arrange them in ascending order of their frequency. Ascending order of the frequency. Right. Now, according to Planck equation, E equal h nu. No? Nu is the frequency. Frequency. Now you can see energy is proportional to the frequency. So if it is having a higher energy, higher frequency will be there. Okay, then how do we get an idea about the energy? You can see these are energy levels. So the transitions among them represents the energy. Okay, so if this length of the arrow is higher, if the length of arrow is higher, you can say energy of that transition is higher. So what is the longest arrow we can see here? From 4 to 2b, no? 4 to 2b. Then you have a little bit shorter arrow d. Then you have a, and finally c. So this must be the order of variation of the frequency. CADB answer is answer 3. Okay, is that clear, Lama? So you have to draw the energy levels in this way, then only you will see the proper gap. You know that the energy gap between 1 and 2 is very high. Then the energy gap is gradually decreasing. Okay, so that's what happens with the energy levels. So it's a very simple one once you draw the diagram. Okay, don't do these questions in other ways. So this is the best way. Okay, now just remind it. We have done plenty of these questions in our previous practice papers. The thermal decomposition temperature of metal carbonates increases downward the group. The correct statement which explains the reason best is asking you to explain the correct reason for the increase of thermal decompositions like this. Sorry, increase. Okay, so that is coming from the bonding lesson. So all the questions we did up to now, the first 4 questions are from atomic structure. So now let's see this question which is coming from bonding. And it's actually about the ionic bonding. So metal carbonates, group 2 metal carbonates are beryllium carbonate, magnesium carbonate, calcium carbonate, strontium, and barium carbonate. So you can look at a periodic table and write this. Barium carbonate. So these are the group 2 carbonates. Okay. And it says their melting point, so the thermal decomposition temperature increases downward the group. Thermal decomposition temperature increases downward the group. They are asking for the explanation. Okay. So let me tell you the full theory of this one. If in case you have forgotten this, now you can remember. Okay. So if the thermal decomposition temperature is getting higher, that means this compound will become stable downward the group. That's why it is difficult to thermally decompose. Which means again, this magnesium carbonate, calcium carbonate are weaker, while barium, strontium, those are stronger. That's why it is difficult to break the bond. That's why it is difficult to thermally decompose. Understand? So that means what is the bond among these compounds? You have ionic bonds among compounds. No? Ionic bond between the metal and the carbonate, you have an ionic. You have this ionic. Okay, so the ionic bond will become strong. Okay, so you can say bond nature, or you can say simply ionic character. Ionic character of bonds increases. Ionic character of bonds between increases. What is this bond I am explaining here? Ionic bond between metal and carbonate. Carbonate is an anion. Metal ion is our cation. Positive, negative. Electrostatic attraction. Okay. Right. So it tells this this is becoming stronger. This is becoming stronger. Now you are going to our polarization power and polarizability explanations. Okay. So the anion is same. Anion is same. Therefore, polarizability is same. So we can write anion is same. Therefore, polarizability is same. Here, my cation is changing. Cation is changing. Therefore, polarization power. Okay, we can say about the first of all cation, what is changed. cation, we can see the charge is same. Cation charge is same, but you can say radius or size increases downward. Downward size increases. Therefore, what will happen to the polarization power? Polarization power decreases. As the polarization power decreases, covalent character decreases. Then what will happen to the ionic character? Ionic character will increase. Okay, so therefore thermal decomposition temperature will become higher. So what is this polarizing power? Let me explain that one also for you. When you have a very small cation, it is very likely to attract the electron cloud of this anion. It's very likely to attract this. So that means covalent nature will be higher. Okay, so that means it can finally convert this one into something like this. But if the cation is larger, let's say you have a larger cation, then it is very difficult to polarize. Still, anion will look like a normal spherical anion. Okay, so if the size is higher, it is difficult for the cation to attract the electron cloud of anion. So here it was possible because the nucleus and the anion electron cloud distance is very little. But here now the distance and the distance between the nucleus and the anion electron cloud is very large. So it's kind of difficult to polarize this. Okay, so it can be explained. Okay, Lama. So the answer will be, you have to check the answers and see. I have taken the answer as answer 4 here. Let's look at the fourth answer. The polarization power of the metal cation decreases downward the group since the cation size increases. So that is the proper explanation. You can see. Now, write the explanation in the board in your review. Okay, now let's discuss this question about molecular geometry and shape. Right, so the three molecules are XTF2O. The other one is FI. Yeah, FiO3 2 minus. FiO3 2 minus and IBr3O2. IBr3O2. So now first thing you have to do is identifying the central atoms. We know the least electronegative atom is the central atom. Okay, so look at the first molecule. The least electronegative atom is xenon. Okay, so that is the central atom here, xenon. And then other molecules will be around that. So 2 fluorines and 1 oxygen. Okay, so drawing only 2 will be enough. We'll see. Let's start from the first one since it is MCQ. So then you can go with our usual Lewis method if necessary, or you can go with the practice method also. Right? I'll show you how to do this one using the usual Lewis method first. So find the valence electrons. Xenon is a group 18 element which can form bonds, and there are 8 electrons for the xenon. Okay, and then you have 2 fluorine atoms. So 2 into 7, 14 electrons. Then you have 1 oxygen. It has 6 electrons in the valence shell. Altogether, you have 28 electrons. 28 electrons. Okay. From those 28 electrons, you have represented 6 here as 3 bonds. Okay. You have 22 electrons then. That means 11 electron pairs. 11 electron pairs. Okay. So those 11 electron pairs you can represent here. 9 electron pairs can be represented. So other 2 electron pairs you have to put it on the xenon. Right? So now check whether the octet is anyway completed, and then check the charges. Okay. So here you will have a negative charge, and then here you will have 1, 2, 3, 4, 5, 6, 7, a positive charge. To cancel that positive and negative charge, what you are going to do, you're going to make another bond from this. Okay. And then the final structure will be xenon. There will be a double bond here, and there will be two lone pairs. So what is this structure then? Okay, you can see how many repulsion units around this. Okay, you can see there are 5 repulsion units, 5 VSC PR units. So if there are 5 VSC PR units, it is trigonal bipyramidal. Then if one lone pair exists, so therefore shape is, sorry, not one lone pair, 2 lone pairs are existing. Therefore shape is T-shape. Okay, T-shape. Then you can see our answers. Find the answers that are starting from the T-shape. Find the answers that are starting from the T-shape. You can see the second and third answers are starting from the T-shape. Then you can see the second option in those answers are seesaw. That means FiO3 2 minus molecule must be seesaw. So no point of drawing that in the exam. And just draw the last molecule to confirm the answer. Draw the last molecule to confirm the answer. What is the last molecule? IBr3O2. IBr3O2. So central atom will be iodine. Then you have 3 bromine atoms. 3 bromine atoms and 2 oxygen atoms. So I have used the practice method. Usually when halogens are there as the peripheral atom, they make single bonds. If they make multiple bonds, they will have charges. Then if it is oxygen, usually it makes double bonds. There are no charge in the molecule, right? So it must make the double bonds there. Then check the electrons around iodine. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 electrons are there. So then you have again 5 VSCPR units. So then shape and geometry both will be trigonal bipyramidal. Trigonal bipyramidal. This is the geometry, electron pair geometry. And shape is T-shape in the first molecule. And the last molecule, shape and electron pair geometry both will be trigonal bipyramidal. So answer is going to be answer 2. Okay, answer 2. Then for the completion of our review, we'll draw the second molecule using our practice method. Iodine is the central atom. You have 1 fluorine and 3 oxygen. You can see the negative charge is there. So negative charges are there on oxygen. It's the usual way. It must be there on oxygen. Then if they are keeping the negative charge, they make single bonds. Then you have the third oxygen with the double. And check now how many electrons are there around iodine. 1, 2, 3, 4, 5. Then you have to put another 2 as a lone pair. Okay, then 7 electrons will be there. So this is going to be seesaw shape. See, 1 lone pair and 4 bond pairs. Seesaw. Yeah, that's a question that you should not miss. Okay, practice Lewis structures very well. So let's say you don't have any good idea regarding the Lewis structure. Now you have forgotten the things. Please get the recording and study. Okay, the recording and study. You have the resources now. Use it. Right, now look at the 7th question. The increasing order of the ionic radius of the ions, lithium, arsenic, and there are several ions given. You'll see how to do that. First of all, use the periodic table and find the locations of these elements. That's where you should start. Get the periodic table and find the locations of these elements. Now, these elements, lithium plus ions are lithium plus arsenic 3 minus. And then you have P3 minus. Then you have selenium and sulfur. These are the elements. These are the ions actually. So, and if you take the periodic table, you can find these elements here. Lithium in the first group. This group and the second period. Then in the third period, you can find phosphorus and sulfur. Phosphorus and sulfur in the third period. In the fourth period, you will find arsenic and selenium. This is how these elements are there in the periodic table. These are there in the adjacent groups. This is there in group 17, so group 15, group 16, and this is there in group 1. Okay, so now group and periods are shown in the diagram. Lithium is in the second period. No? So lithium plus should be the smallest one. Lithium plus should be the smallest one. Okay, lithium plus should be the smallest one. Then you have other four. So remember these four they are in the adjacent four boxes. So their radius is variation in this way, mirror descent. Remember that is a theory point I taught you, mirror descent. So that means the smallest one here will be sulfur, then phosphorus, then selenium, largest will be arsenic. And here I wrote about the elements, but their ion radii will be also changing in the same pattern. Same pattern. So S2 minus, P3 minus, selenium 2 minus, and arsenic 3 minus. This must be the answer. I have to apply mirror descent. Okay, write that too, just to remember. Mirror descent. Because he said we are writing in this way, no? That he said we are getting in this. Okay, so actually in mirror descent, there is nothing more difficult, right? In mirror descent, it is explaining that the downward the group radius increases and across the period it decreases, no? Downward the group increases, across the period decreases. So here arsenic and selenium should be larger than other two because they are in the lower period, no? And arsenic should be larger than selenium because it is further to the left in the same period. Okay, that's the logic. There's nothing more. Right. Answer is going to be answer 1. Answer 1. Then let's go to the next question. Question number 8. That's a good one. There are 5 statements different to each other, which is coming from both atomic structure, bonding, and everything. Okay. So it's asking for the incorrect statement. Incorrect statements. Let's review that one properly. Look at the first statement. The electromagnetic wave responsible for the 4 to 1 transition is in the visible region. So remember that 4 to 1 transition, 4 to 1 transition in equal 4 to 1 is there in Lyman series. Lyman series. Okay. So Lyman series is in which region? In the Lyman series belong to the ultraviolet region. Okay, so therefore first one is incorrect. It says it is in the visible region. That is incorrect. So all transitions, all electrons falling back to first energy level belongs to the Lyman series. Okay, you can say all falling back to the first energy level. All electrons falls to first energy level. They belong to the Lyman series. Okay, and those will be belonging to the UV region. Lyman belongs to the UV. So who's belonging to the visible then? Balmer, no? Balmer first 4 lines are in the visible region. So it's wrong to say it is in the visible region. So this will be our answer. Okay. But in this question, when we review, we will see there is another answer. There's another incorrect statement. There is the second statement. Look at that. In this question, there are 2 answers. So among the species NO43 minus, NO43 minus, and then NO3 minus, and then NO2 minus. These are the ions given. Least stable is NO2 minus. Okay, it is not the least stable one. To get an idea about the stability, we will get the Lewis structures. Lewis structure of NO2 minus is this. Okay, there is no that much unstable nature is seen, no? It's a good one. And NO3 minus, normally okay. But look at the NO4 3 minus. This is the unstable one. You will have a tetrahedral molecule, ion, tetrahedral ion, and each oxygen will contain a negative charge. And nitrogen will contain a positive charge. Here the problem is this is unstable due to high charge separation. High charge separation. That is the problem. That is the problem. Okay. So second statement is also wrong. NO4 3 minus is relatively unstable than the other two. Okay. Now look at the third statement. We will review that too. In third one, it is telling among the species ammonia, NF3, NCl3, the highest electronegative nitrogen can be found in NF3. Highest electronegative nitrogen can be found in NF3. NF3. NH3, NF3, NF3, and NCl3. NCl3. These are the molecules. Highest electronegative. Okay. So then these all are trigonal, sorry, tetrahedral geometry, trigonal pyramidal shape. Okay. Tetrahedral. So their S percentage will be sp3. S percentage is sp3. S percentage is sp3. sp3, then S percentage is going to be 25% since they are sp3 hybridized. All are sp3. And then since their hybridization is same, you have to go to the charge. Then they don't have any charge. And then you can go to the oxidation number. Oxidation number is going to be here nitrogen -3. These two will be +3. And then you have to go to the peripheral atom electronegativity, that is fluorine. Then peripheral atom electronegativity is higher for the NF3. Okay, so this is oxidation number. Then your answer is going to be NF3. NF3 is the most electronegative one. Okay, that is correct. Most electronegative nitrogen is there for the NF3. So refer those notes again, right? If you have any doubts. Then look at the fourth one. Increasing order of the polarizability of ions. Polarizability of anions depending on their charge and size. Okay, if the anion is a larger one with greater size, greater size and greater charging, then it can be easily polarized. Okay, that anion will be easily changed when there is a cation to attract those electron cloud. Okay, so then polarizability is higher when the anion is larger and their charge is higher. So from these three ions, it is given N3 minus, O2 minus, and P3 minus. So what is the largest size and largest charge is there for the P3 minus. So P3 minus polarizability will be the highest one. Then N3 minus and O2 minus. O2 minus is small and low charge. In this direction, you can see charge and size increases. When charge and size increases, polarizability getting higher. At the fifth one, the ability of CO2 gas, ability to liquefy CO2 gas is evidence for the existence of London forces. Existence of London forces among nonpolar molecules. That is correct. Okay, so CO2 can be liquefied by cooling and compressing. That means in a liquid there are intermolecular attractions, no? The better ones. That means that nonpolar CO2 has made intermolecular attractions. So that intermolecular attraction must be what? London forces. Okay, London forces. That's a good evidence to prove that even nonpolar molecules can make attractions. The ninth question. Ammonia can be synthesized at high temperatures as shown by the following unbalanced chemical equation. Balanced chemical equation. Ammonia. NO reacts with H2 to form NH3 and water. Okay, so first of all, we need to balance this, no? First of all, we need to balance this. Then anyway, the other data they have given, ammonia, they're asking how much of grams of ammonia can be synthesized from 60 grams of NO and 15 grams of H2. 60 grams of NO and 15 grams of H2, and they have given as data the relative molecular masses. Okay, like I said, let's balance this one first of all, right? So we are using the inspection method to do this one. And here NO, NH3, hydrogen, you have 5 hydrogen atoms here, no? So that means can start by putting 5 over 2 here. But we can't put fractions, no? We can't put fractions, no? So then we multiply the whole thing by 2 to remove that fraction. So then it will be 2NO reacts with 5H2 to produce 2 ammonia and 2 water. Okay, you can see the hydrogen. Now it is 10. In the other side also 10. 2 nitrogen, 2 oxygen. So it's balanced. So this ratio is important for us. How they react. 2, 5, 2 and 2. They're asking about this ammonia. Okay, so remember to look at this. Since they have given data about 2 reactants, we are not sure about whether NO or whether H2 completely finished. Okay, so to find that, we have a method to do that is called ARR method, added, reacted, and remaining method. To use that one, ARR method, to find actually who's the limiting reactant out of these two, NO and H2. So for that, we need the moles, because ARR method is applied for moles, no? So moles of NO is equal to 60 divided by 30 grams per mole. 30 is the that is given in the paper as the molar mass, 30 gram per mole. So you have 2 moles. You have 2 moles. Then find the moles of H2. 15 grams divided by 2 grams per mole. That's the relative molecular mass of H2. So you have 7.5 moles. So we have 2 moles and 7.5 moles. Then let's say like this, okay? So NO to H2. NO to H2, okay? They react in 2:5 ratio. So this is the stoichiometry ratio. Stoichiometry ratio. So then see the added ones. If you are reacting with 2 of this one, then 10 of this must, not 10, 5 of this must be reacting with this. Okay, so this is available. But see this 7.5 thing. If you are reacting this whole 7.5, how much is needed as NO? You have to find it by dividing 7.5 by 5 for the own stoichiometry and multiplying by the required stoichiometry, which is 2. Okay, so you need 3 moles. So you don't have 3, so therefore this ratio is not going to work. Okay, so therefore this 2 added will fully react with the 5 of this and 2 will be formed here. Is the reacted and remaining, nothing will be remaining. Here 2.5 will be remaining. So this is called our limiting reactant. And here 2 moles of ammonia will be formed. We need the mass of ammonia. For that, what should we do? Multiply this number of moles by their relative molecular mass. So 2 moles into 17 grams per mole. Okay, so that means 34 grams. 34 grams. Answer is answer 3. Okay, 34 grams. So we applied ARR method in the 9th question. In the 10th question, what is the method we are applying? Remember the other type of question we had in our chemical calculations? That is stoichiometric bridge. Stoichiometric bridge concept. We'll apply that method to find the answer. Find the answer of the 10th one. Okay, see, 0.6 grams of KiO3 is dissolved in excess Ki. So it is excess, no? So that means that 0.6 KiO3 is fully reactive. In exam, it is asking the minimum volume of 3 mole per decimeter cube HCl required to completely convert KiO3. Yeah, there is a third reactant also. So let's take the reaction anyway. HCl reacts with KiO3 and Ki to form I2, KCl and water. Yeah, you need to balance this one first. Stop that, talk about that after the balance. Right. So KiO3, Ki, I2, KCl and water. Okay, let's see. So here, yeah, start with the iodine. No, oxygen. Here you have 3 oxygen. Then let's put 3 water. And if you had 3 water, then there are 6 hydrogen atoms. So this will be 6 HCl. If there are 6 HCl, this will be 6 Kc. Okay, see the way we are going. Then if there are 6 KCl, you have to put that 6K, no? I can't put any number in front of this, then the whole thing will be changed again. So let's put 5 in front of this Ki. Then 5 and this one will become 6K. And then you have 5i and 1i here. So it's going to be 3i2. Okay, so I'll show you the way we started from here to here, the first one. And then we go to the 6HCl, the second step. And then we came from this there to put the Cl thing. And then from 6K to, then we went here. Fourth step. And then finally, we came to this as the 6th step. Okay, so however, we have this balanced equation. So I'll write that again. 6HCl react with KiO3, 5Ki goes to 3i2, 6KCl and 3 water. Sorry. So now we are adding this one excess. So nothing to worry about this. And yeah, 0.6 grams of KiO3. So mass of KiO3 is given 0.6. And then we can find moles of KiO3. Then you can go to the moles of HCl using the ratio. And then you can go to the volume of HCl. That is the flow. That is the flow. Okay, so mass of KiO3. 0.6 grams are there. And the molar mass of KiO3 should be found. Potassium 39, iodine 127, 3 oxygen means 48. You add them, 9 plus 7, 16, 24. 5, 9, 11, 240. Okay, now it is not divisible, no? So moles of KiO3 will be 0.6 divided by 214 moles. So don't go to divide this one because it is a MCQ. There will be a way of finding the answer quickly. Right, and then here you need to multiply by 6 now because one of this will react with 6 of this. Okay, so then we can find the moles of HCl. Moles of HCl is equal to 0.6 over 214 into 6. Okay, then it is asking the volume. So how do we get the volume? C equal N over B. Therefore, V equal N over C. V equal N over C. We know the moles, and volume of HCl can be found by dividing it from its concentration. Concentration is 3.0. And the thing is, you are getting the volume in decimeter cube. Here you can cut one. That's why I said wait. Here you can then divide 1.2 divided by 214 into 1000. Then you will get the answer in centimeter cube. Okay, so 1200 divided by 214. So if you divide it by 200, it will be somewhere around 6 now. Then it is less than 6. Less than 6, it is somewhat closer, somewhat there in between 6 and 5. So there is only one answer, 6 and 5. Answer 3. Okay, that's why I'm asking you not to simplify in the middle for the MCQ. Sometimes it is easier this way. Now let's quickly discuss this structured essay 1. Right, look at the first one. The wavelength of electromagnetic wave relevant to the transition from n equals 6 to 3. Okay, wavelength of the transition from 6 to 3. 6 to 3. 6 to 3, and what is the other transition they are expecting to compare here? 4 to 2. Okay, 6 to 3 and 4 to 2. 1, 2, 3, 4, 5, and 6. 4, 5, and 6. 6 to 3, 4 to 2. 6 to 3 and 4 to 2. Okay, look at this one. 6 to 3 is the transition like this. 4 to 2 is a transition like this. Now you can see here the second energy level. This is a Balmer series line. Balmer series is in the visible region. That means energy is higher. Wavelength is lower. Okay. And in this one, this third energy level. Third energy level falling things are there in the Martian series. Martian series in the infrared region. Infrared region, energy is lower. Wavelength is higher. Energy is lower, wavelength is higher. Remember the relationship between energy and wavelength equal hc over lambda. From the Planck equation, you can see how energy and wavelength is related. So look at the statement then. It says wavelength of electromagnetic radiation relevant to the 6 to 3 transition is greater. Yes, that is greater. Statement is true. Energy wise, it is having low energy, and therefore wavelength is higher. And this visible region line 4 to 2 is actually the color is green. Green. Because 3 to 2 is red. First line is red, second line is green. 4 to 2. Third line 5 to 2 is blue, and 6 to 2 violet. Like that, remember the others also. When you are writing the name, you can add them too. Okay, that will be nice. So first is statement, answer is true. Then look at the second one. First is statement, answer is true. Now look at the second. There are only 7 electrons in potassium atom with the azimuthal quantum number L equals 0. L equals 0. Let's write the electronic configuration of potassium. 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. L equals 0 means lamai S sub energy level. S sub energy level. You can see S sub energy level electrons here, 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 and right here. So you have 2, 2, and another 2, and 1. So you have 7 electrons. So that statement is also correct. Azimuthal quantum number L equals 0. You have 7 electrons. That's true. Okay, you can write L equals 0 means S sub energy level. S sub energy level. Right. Look at the third one. Number of unstable Lewis structures for the bicarbonate is 2. Bicarbonate. HCO3 minus. So let's say why it is false. Unstable Lewis structures. We have to draw the Lewis structures or the resonance structures of the bicarbonate. HCO3 minus. So I gave you the skeleton there. Without the skeleton, it is difficult for you to do this now. And we know when we draw the resonance structures, simply we can change the location of the phi bond like this. And then we can draw one more structure by putting the phi bond to this oxygen connected with the hydrogen. And interestingly, there you will be having a positive charge. So having positive charge on the more electronegative oxygen make it unstable. And these two are stable. So this question is telling there are two unstable structures. No, there is only one unstable structure. And write why it is unstable also. More electronegative oxygen has the positive charge. That is the problem with the third structure. That is that structure is unstable. Okay, Laman? Is that clear? Right? So now we can go to the fourth state. Let's see why it is incorrect. So let's see whether it is correct or wrong first of all. Among group 17 elements in the periodic table, fluorine has the highest value for the electron affinity. It is not fluorine. Electron affinity means likeliness to the electrons, no? Right? In group 17, electron affinity changes in this way. You need to remember that. Electron affinity changes. Chlorine is the highest affinity. Then you have fluorine. Then you have bromine and iodine. Chlorine is the one with the highest affinity. Why? Because it is having the optimum size. It is having the optimum size. So fluorine, it is too small. Too small. Therefore, electrons are crowded. Okay? Electrons are crowded. Existing electrons repel the new. Repel the new one more. There is a problem with the fluorine. Therefore, the affinity of fluorine is low. Bromine and iodine, they are too large. So therefore, affinity is even lesser. Because the new electrons is weakly attracted to the nucleus. Okay. Right. So then fourth one is false. Right. Now let's look at the fifth statement. Fifth statement. The melting point of lithium is higher than that of sodium. Melting point of lithium is higher than that of sodium. So it's about metallic bonds. Fifth one. Metallic bonds. Sodium, lithium. So these are group 1 elements, no? Lithium, sodium, potassium, rubidium, cesium. melting point decreases. Melting point, you can say melting point decreases downward the group. Decreases downward the group. So why it is happening like that? Because the melting point of metals, right, depend on their strength of the metallic lattice. So metallic bond become weaker for these 5 elements downward the group. Okay, you can say the reason size of metal ion increases. Size of metal ion increases. Therefore, lesser number of metallic bonds. Lesser number of metallic bonds in unit volume. Lesser number of metallic bonds in unit volume. Okay, so that is the problem. That is the problem. Okay, so melting point of group 1 elements decreases downward the group. Lithium, the one with the smallest size, is the one with highest melting point. Okay, so fifth one is yeah, correct. Says lithium is higher than sodium. That is true. Look at the sixth one. Oxygen has the highest second ionization energy among the elements CnOF. You check that now. CnOF, highest second ionization energy. So first ionization energy variation we had to use for that. It is taken as true here. Let's see the explanation. Fluorine, oxygen, nitrogen, and then carbon. These are the first ionization energies. No? So second ionization energy is simply taken by coming one backward because it assumes the previous element electronic configuration. So F plus will be right here and O plus will be here, N plus, and C plus will go one further down. So now you can see oxygen is the one with the highest second ionization energy because O plus is having the stable nitrogen configuration. You can say O plus has the stable nitrogen 2s2 2p3 configuration. Okay, nitrogen configuration. You can tell that. Okay, students. Now that is the answer for the explanation for the sixth one. It says oxygen is the highest second ionization energy. That is also true. Okay, so that's the explanation for the first 6 statements. You can see they are not that easy. You have to think well and process to get the answers. That's why I said the paper is also a good paper, right? And this is a very good chance to fix your mistakes. Okay. The first one is about the Lewis structure. Draw the most acceptable Lewis structure. So I'll guide you how to get that Lewis structure using our Lewis structure method. These things you have to master really well. Remember that. Still there is time to fix your problems now. So get the benefit of the recordings and these classes we provide you and improve yourself. Okay. Finally, we should have results, no? So F, what is the skeleton structure? F, C2, C1. Then we have nitrogen, fluorine, and another fluorine here. Draw the most acceptable Lewis structure. Draw the most acceptable Lewis structure. So there is nothing, any other statements given. It says it is a molecule. It is a molecule. That word is important. Remember, if they says it is a molecule, that means it is having no charge. No charge. If it is a molecule, there is no charge. Okay, with your practice, you can draw this easily, but I'll show you first how to do it with the Lewis structure method. First, get the number of valence electrons. There are 3 fluorine atoms. So 7 into 3, 21 electrons. And then there are 2 carbon atoms, 8 electrons. And there is a nitrogen atom, valence electrons are 5. So if you add them, 26, 34. From those 34 electrons, you have to subtract 1, 2, 3, 4, 5. There are 5 bonds, so 10 electrons. 4, 5 bonds in skeleton. So then you will be left with 24 electrons. So divide that 24 by 2, and then you will get 12 electron pairs. Those 12 electron pairs you have to distribute. Okay, those 12 electron pairs you have to distribute. So start from the fluorine, which are the peripheral atoms and most electronegative. You can put 3, 6, and 9 electron pairs to that. So there will be another 3 remaining. Those 3 you can put 1 to the nitrogen, because it is the second most electronegative element here. And other 2, you can put 1 for each carbon, or you can put just 2 for the both carbon, no problem. 1 carbon, right? And here then the next thing is you are checking the octet. Nitrogen octet is completed, but carbon and this carbon octets are not completed. So don't stop here. I saw some of your papers. You have stopped here without going forward. So that's a mistake, right? Check whether you have completed the octet. You must check that. You can see now the octet is not completed. So therefore, you must make a bond here. Okay, and then you must make another bond here. Okay, so then there will be a triple bond. Always show all the lone pairs. Okay, then you will not miss any marks. So this is the Lewis structure. So even with your practice too, you can draw this in like this. Now you have this C, F no. So fluorine always makes single bonds. And then to have no charge on nitrogen, there should be a lone pair. Just remember NH3. Now you draw NH3. It is kind of similar to NH3. And then this another fluorine here, it always makes single bonds. And then to complete the octet between these 2 carbon, you have to put 2 5 bonds. That's it. Like that, you can easily get the structure also with your practice. But before that, if you are still getting mistakes here, just practice more with the Lewis structure method and practice more our already done questions. Then you will get to a good place. Okay, don't worry. And so it's asking secondly about the electron pair geometries and shapes. First one, shape around the C1 and nitrogen. C1 here is linear. You can see 2 repulsion units right there as the review. It is having 2 repulsion units, and that's why it is linear. Then the shape around nitrogen is trigonal pyramidal, or you can just say pyramidal, no problem, because there is a lone pair and 3 bonds. Altogether, you have 4 repulsion units. If you are having 4 repulsion units, it is tetrahedral. And if you are having 1 lone pair, it is trigonal pyramidal. So, everyone, goodbye, study well. And if you are having a free day today, then use the rest of the time of the day to go through the paper and repeat these reviews and make a nice note on this. Okay? Right. So then, goodbye, study well.